Okay, so we're starting off the material for the new exam, and this has to do with coupling reactions. Okay, so I don't know if I got my pen. I don't think so. Okay, so coupling reactions. So I don't know if you guys remember the whole energetically favorable, energetically unfavorable. So I'll write down notes right here. We can write in blue. So let's remember, when a reaction has a positive delta G, what does that mean? It is not spontaneous and it is energetically unfavorable. So it costs energy. Now, when something has a negative delta G, it is energetically favorable. So one of the things that is energetically favorable is ATP hydrolysis. So remember, that's adenine with 3 phosphates groups. Now, ATP hydrolysis, what is that? Well, we just have to remember that that's when you have a water molecule who comes in and breaks a bond. So here we're breaking this bond and then we end up with inorganic phosphate. But when we broke that bond, there's actually a lot of energy in that bond. And so what ends up happening is we can couple an energetically unfavorable reaction with this energetically favorable reaction, and we can make it happen. And this is actually how a lot of reactions happen in our bodies. Now, another thing that we have to consider is ratio. So they're going to be asking us a lot about this ratio of Y to X. Now, the reason why they care about the ratio of Y to X is because Y is products. So this is products over reactants. Okay, so whenever you have a reaction that goes from X to Y, Y is the products. And X is the reactants. So if you have a lot of products, like a lot of products, and so your ratio of products to reactants is really high, then that means that the reaction is moving forward. And that means that you have energetically favorable, which means that your delta G is negative. You have to be able to make full circle that connection. Okay, and so we're going to go ahead and practice it. So here it says the ratio of Y to X at equilibrium is equal to the equilibrium constant KEQ. So this formula, you're going to have to like really become comfortable with it. We have ln of KEQ is equal to the negative delta G standard divided by RT. So R is just a universal gas constant and T is the temperature in Kelvin. So they usually don't give you the temperature in Kelvin, so make sure that you know how to convert. And this is one of those things that I'm telling you, make sure you know how to do that. Don't ignore it, and then on the final, you don't know how to do that. Make sure you know how to convert from Celsius to Kelvin. Okay, so here, they're saying coupling so this is what a potential question could look like on your exam. Coupling ATP cleavage, that's just when we broke that phosphate bond. So ATP cleavage to an unfavorable reaction. We know that this whole ATP cleavage was the favorable reaction. Make sure you label things for yourself. Okay, so that's what I'm doing. So ATP cleavage was the favorable reaction. And this had a negative delta G. Okay, so when you couple ATP cleavage to an unfavorable reaction, so what do they mean by unfavorable? Well, that just means that we have a positive delta G. So to explore the consequences of coupling ATP hydrolysis under physical conditions to a thermodynamically unfavorable biochemical reaction, consider the hypothetical transformation of X to Y, for which delta G standard is 20 kilojoules per mole. So notice the units, this will always have to be in kilojoules per mole. So one of those things you have to kind of memorize. So what is the ratio at equilibrium? So anytime somebody asks you for the ratio of something, you use this formula. Ln of KQ is equal to negative delta G divided by RT. So we know that our negative delta G was 20 kilojoules per mole, and it was positive. Whenever I don't see the positive sign, I draw it in, because I need it to be blatantly obvious to me. So we just have, don't forget your negative sign here, because that one was already there. And then we have 20 kilojoules per mole divided by, here they didn't give us a temperature, so they just assumed that they did, which is fine. On the exam, you're going to get a temperature. So here the temperature times R was 2.48 kilojoules per mole. And so our ln of KQ is equal to -8. So now in order to get rid of the ln, you just write KQ is equal to E to the power of your answer. So E to the power of -8. And that will equal 3 times 10 to the -4. And this is the ratio of Y to X. So we know that the ratio of Y to X is products to reactants. So what number is 3 times 10 to the -4? Well, you just go back 4. So this number is actually 0.0003. So the number of product is really, really, really small. So this is a very small K equilibrium. Consequently, delta G is large and positive. So you see that here the reaction is not moving to the right because the concentration of product is super small. So that means that the reaction is either moving left or just staying still. The delta G is positive. That's what matters. If the ratio of Y to X is small, delta G is positive, and that means that this is energetically unfavorable. So now we're actually going to couple mathematically. So suppose X and Y in a sequence of reactions during which ATP is hydrolyzed to ADP and phosphate. The overall reaction is X plus ATP. Okay, this is what we have to pay attention to. They are going to be giving you something like this on the exam where it's X plus ATP plus water turns into Y plus ADP plus phosphate. So now I like to highlight my arrow because you know me, I like to color code everything and organize it so I don't make mistakes. Okay, so I have my arrow and now I'm going to start labeling. So these guys back here, these are all my reactants. And these guys here, these are all my products. Now, I'm going to be coupling two reactions here. So it's your job to pull out what goes in one reaction versus what goes in another reaction. So in red, I'm going to pull out the stuff that goes in one reaction. So for me, ATP is easy. So you need ATP. You also need water because water is what comes in and breaks that last bond to get rid of that phosphate. And then what does that turn into? Well, that leaves behind as a product ADP instead of ATP, and then you have inorganic phosphate. So that's all one of our reactions. Okay, now we have to grab the stuff for the other reaction. Well, that's X and Y. So X turns into Y. Okay, so whenever you see an exam and you see coupling reactions, will you be able to take out the two reactions? That's step one. Yeah, you feel comfortable with that? Okay, so now the next thing you do is organize them. So here's reaction 1 and here's reaction 2. And you see how we just took X turns into Y. And then over here we wrote down ATP plus water turns into ADP plus phosphate. Okay, perfect. And then the next thing I like to do is I like to draw another line. So anything behind this line are my reactants, and anything after that red line are my products. So when you write down the sum, you write down all your reactants. X plus ATP plus water turns into ADP plus phosphate plus Y. And then over here on the right-hand side, they have the delta G's. So standard free energy changes for each of these reactions. So we were told that to go from X to Y, the standard free energy was 20 kilojoules per mole, and that was positive. Now here in the problem, they're telling us that the standard free energy change for ATP hydrolysis is negative 30.5 kilojoules per mole. So you're given both of this information. Okay, so now to take the sum of the free energy, all you do is add these. So plus 20 plus a minus 30.5 gives you a negative 10.15. So we know that if we have a negative delta G, this is going to be energetically favorable. So whenever we do this kind of math, we remove water. Water does not participate in the math. And then on an exam, they can ask you for the ratio. So they can say, calculate the ratio of X over Y or products over reactants at equilibrium. They could say that at equilibrium, or they can say, calculate this under physiological conditions in a cell. And if they tell you in a cell, they'll usually have a little table with like 5 different cells and then all their values. And they'll specify which cell. You have to go to the table, grab the cell, and you take those values, and those are the ones that you plug in. Okay, so we're going to do an example of both. This first example is at equilibrium. So on the final, they're not going to be telling you, like they're just going to give you hints. So they're either going to say at equilibrium or they're going to say under physiological conditions. You have to know what to do. This is what I mean, terminology, rules, all that. If they say at equilibrium, then what they mean is that for ATP, for ADP, and for phosphate, these are all at 1 molar concentration. And that's fantastic because it makes our math easier. So we like equilibrium math. We like that, okay? So the next thing you do is you set up your equation. KQ is equal to, and then this looks like a new equation and it looks scary, but it's not. It's the same old equation. It's just KQ is equal to products over reactants. You guys remember that? Okay, so all they're doing here is they're saying our products, if we remember our products over here are Y, ADP, and phosphate. So you just do Y, phosphate, and ADP. They don't have to be in the right order. I like to keep them in the right order, so it's up to you how you want to write them down. But basically, you just write down all your product concentrations, and then below that, you write down your reactant concentration. So that's just X and ATP because we know water doesn't count. Okay, and then what they told us, because this is equilibrium, we know that phosphate is just 1 molar, ADP is 1 molar, and ATP is 1 molar. So really, we can cross all this out. And our KQ is equal to the Y over X ratio. So that makes our math really easy, huh? So then we can go ahead and use this one where it says, we go back to our original equation that we started with. ln of KQ is equal to negative delta G divided by RT. So here we have equals, so we write our negative, and this time our delta G was minus 10.5 kilojoules per mole after we went ahead and combined the two reactions. This was our delta G. So that's the value that we plug in here. And then when we did R times T, it gave us 2.48 kilojoules per mole. So our answer was 4.23. But remember, our answer is an ln of KQ. We still have to get rid of that ln. So in order to do that, all you do is you get E and you raise it to the power of 4.23. And that will give you 68.7. So 68.7 is our ratio of Y over X, or products over reactants. So last time our ratio was only 0.0003 for products over reactants. So we knew that the reaction was not moving forward and the delta G was positive. But now our ratio is really high. Look at 68.7. So you have 68.7 times more product than you do reactants. So we know that the reaction is moving forward. And this means that the delta G is what? Is negative, right? So you have to be able to go full circle with this stuff. So this coupled reaction is very favorable as it is written. Okay. So now we're going to do an example problem where it's under physiological conditions. Okay, so we know that ATP, ADP, and phosphate, they're not 1 molar under physiological conditions. Calculate the Y over X, or product over reactant ratio, for the ATP coupled reaction when the values of ATP, ADP, and phosphate are those found in rat myocytes. So they give you a table, and then they give you the concentration. So for ATP, we have this for ADP, and phosphate this. Notice that they gave us everything in millimolar. Is that acceptable for our formula? No, our formula only accepts molar. So students still struggle with converting. So the easiest way to do it is just do 8.05. Now milli is 10 to the negative 3. So just do that times 10 to the power of negative 3. Molar. So you just replace milli with 10 to the power of negative 3. Ah, there's a bug. Sorry. I was sitting under a tree for like an hour and now I'm full of ants and bugs. Okay. All right, so times 10 to the power of negative 3. Okay, and then you do the same for this last one. I'm not going to do it, but basically, so now we do the exact same formula. The K equilibrium is equal to our products over reactants. So for our products, it was just Y, inorganic phosphate, and ADP. That didn't change. And then our reactants was just X and ATP. So hopefully this is all becoming easier now that we're seeing it over and over again, okay? So the one thing that is hard here is that, and I recommend that you memorize this. So look at how they wrote this down. It says if we hold the values of phosphate, ADP, and ATP at the values known to exist in the cell, we can calculate the values of X and Y that meet the equilibrium expression above, giving the equilibrium constant we calculated in B. So here, what they did was they're starting off with this guy and plugging that in, and they're extracting the Y over X ratio, and they're putting it over here. So this, you just have to memorize it because you have to do algebra that I don't remember how to do. to do this. So now you have y over x is equal. So they put KQ right here. And then they just did reactants over products instead of products over reactants. Because you see ATP was supposed to be on the bottom, but now it's on top. And you see phosphate and ADP were supposed to be on top, but now they're on the bottom. So just have that memorized. And then they went ahead and plugged everything in. Okay, so we had gotten for KQ, we got 68.7. For ATP, they gave us 8.05 times 10 to the negative 3 molar. For phosphate, they gave us 8.05 times 10 to the negative 3 molar. And for ADP, they gave us 0.93 times 10 to the negative 3 molar. Okay, so once you know how to do this conversion, then you can go ahead and just plug everything in. So then it's nice and easy. The answer is 7.4 times 10 to the 4th. So that's our ratio of y over x. That's the ratio of products over reactants. So the answer is actually 74,000. Right? So is that number high or low? That's really high. So what does that mean? So the ratio of y to x is really high. The ratio of product to reactants is really high. Well,
It's not really favorable. It's a lot of products.
does everyone agree? What is happening? So what does it mean? Let me rewrite it down for you right here. So we have hold on. Okay, so 74,000 is equal to the ratio of y over x. So y is the products and then x is the reactants. So all of this matters. You guys absolutely have to be able to make the connections. So then over here we have from x to y. So if the ratio of products to reactants is really high, which here it is, it's 74,000, that means that there are 74,000 more products than there are reactants. What does that mean? The reaction is moving in which direction? To the right. And what does that mean about your delta G? It's negative. What does that mean? Yeah, so okay. Let me write that in one sentence. If the ratio of products to reactants is high, then the reaction is moving to the right and the delta G is negative and it is favorable, right? So that's the connection you guys have to make. You have to be able to go full circle. Now, so by coupling the conversion of X to Y to ATP hydrolysis and by holding ATP, ADP, and phosphate far from their equilibrium levels, the cell can greatly increase the ratio of product to reactant. So we want to increase the ratio of the product to reactant, Y over X, because that will mean that the reaction will keep happening to the right. So I've seen this on several exams. This is usually a question that professors love to ask because it shows that you understood everything that we've been talking about until now. So sometimes it'll be something like, how does the cell like not run out of ATP? How does it keep going? Like, how does it keep reactions going? And the answer is that it keeps ATP, ADP, and phosphate concentrations far from equilibrium. It keeps them far from equilibrium. And you can tell this because look at the concentrations they gave us. 8.05 times 10 to the negative 3. What number is that? Well, you have to go back 3. So it's actually 0.00805 molarity. If you go back 3 spaces to the left, because this is millimolar. So 1, 2, 3. So that's 0.00805 molarity. That's really far from equilibrium, right? So that's the secret. That's how the cell does it. It keeps those concentrations really high from equilibrium. So, and that's how it keeps the ratio of Y to X really high to make sure that the reaction moves to the right and that the delta G is negative. Okay, we have enzyme reactions. You guys can memorize that by yourselves because there's one more concept that is really hard. It's one of the hardest concepts for the whole semester. So I want to cover that with you in detail. Okay? So I'll start here. So standard reduction potential. Standard reduction potential. Become best friends with that word. So that's standard reduction potential is usually just E. So this is used with redox pairs. Okay, so if we remember anything about oxidation and reduction, I'll write it right here. Okay, so oxidation equals loss of electrons. Reduction equals gain of electrons. So whenever you have redox pairs, you have pairs of molecules where all they did is one molecule gave the other molecule some electrons. And they like swap them back and forth. And so they become a redox pair. Okay. And this is where we do math for standard reduction potentials. So here we're looking at 2 redox pairs. And you have to be able to identify them. So you have NADH plus H, and that's a pair with NAD plus. Actually, I think I'm supposed to circle the H plus here because it's usually 2 electrons at a time. And then we have lactate and pyruvate, and they are a redox pair. Okay, so the first thing you have to do is get familiar with your redox pairs because on the exam, they'll just give you like an equation like this, and you have to know who belongs with who. That's step 1, okay? Now, there will always be a table. And this table will give you the standard reduction potential values. So for NAD plus, and then NADH. So that'll be 1 pair. And then we'll have, it'll be like down there. And then up here, we'll have the lactate and pyruvate. Okay, so they'll give you all the different redox pairs in a table. And then on the right-hand side, they'll have the standard reduction potential value. Okay, so for lactate, it's minus 0.185. So minus 0.185. And for NADH, it's minus 0.320. So now you have your redox pairs, and then you have your standard reduction potential values. So for this table in your book, it'll be like 15 or 20 redox pairs with all the values. And the way the table's organized is usually the numbers go from positive to negative. So sometimes they'll give you a positive and a negative number. Other times they'll give you two negative numbers. And don't let that throw you off. You have to just figure out which one is more positive and which one is more negative relative to each other. So here it's telling you, what is the standard free energy change? And I'll give you that formula later for the conversion of pyruvate to lactose. The first step is to calculate the change in standard reduction potential for the reaction. So this is really easy. So that's step one. Okay, I'm going to write it down right here. Step one. And this will be step two. Okay, so step one and step two. So to calculate the change in standard reduction potential, all you do is take the standard reduction potential value for the most positive one, and then you subtract the more negative. So for pyruvate and so NAD plus, who's more positive? They're both negative, but who's more positive? Pyruvate and lactate, yeah, because that's minus 0.185. And NAD plus is more negative because it has a more negative number, like a higher, more negative number. It's minus 0.320. So this is more positive and this is more negative. Now that we've identified those, we know that we take the more positive value, which is minus 0.185 volts, and you subtract minus the more negative value, which was minus 0.320 volts. And the answer is going to be positive because you had negative minus a negative number. And then this number was larger, so it turned positive. Okay. So that was step one. So we got the change we got the difference in standard free energies. So we just subtracted one from the other, boom, we got it. So on a test, step one is to figure out who is the redox pairs, then go to your table, get the values for the standard reduction potentials, then figure out who's more positive, who's more negative, so that you know who is subtracted from who. The more positive value minus the more negative. Once you get that answer, you can work on step two. And this is a new formula, so pay attention. You have your delta G minus N. So what was N? N is the number of electrons. So that number is usually 2, but double check with the professor to see if that number will ever be anything other than 2. F is Faraday's constant. So F is equal to Faraday's. And so that's just right here, 96.5 kilojoules per volt. And then delta E, that's just the change in standard reduction potential, which is the number that we just calculated. So you just plug that in. So then you just plug in, you go negative 2 because there's 2 electrons, Faraday's constant, 96.5, and then the delta E, which is the change in standard reduction potential, 0.135. And then so your total answer for the free energy is negative 26.1 kilojoules per mole. So is this energetically favorable or unfavorable? It's favorable, yeah. So the reaction's moving to the right. So this is really easy, right? So the reason it's so hard, it's one of the hardest concepts, is because of all the terminology and because there's new formulas associated. But if you guys are given a redox pair, you should be able to figure it out, right? It's not too bad if you follow these steps. So definitely review this material. Now, it also teaches you how to get the equilibrium constant. So once you have your delta G, you can just go back and use that same formula that we just used. The ln of KQ is equal to negative delta G. We just found that out. It's minus 26.1 divided by RT. So they gave us the temperature. We know R. And so bam, you just divide those two and then we get 10.5. And to get rid of the ln, you just do e to the power of 10.5, and that gives you this number. And this is a really large number. So we just did everything the same. So what I did for you guys here was that I gave you all the definitions. A reduction is a gain in electrons. You become more negative. Oxidation, you lose electrons. You become more positive. What is a reducing agent? You donate electrons. So it reduces something else. Oh, that's one thing I didn't do for you guys. Okay. So I'll put it right here. So whoever is more positive, now we're doing rules. Tend to accept, I'm putting it in capital. You guys have to know this. Tend to accept electrons. And that makes sense, right? Because you're more positive. So you're going to tend to accept more electrons. Now, if you're more negative, that means you already have a lot of electrons. So what do you tend to do? Tend to donate electrons. So if you donate electrons, you are the reducing agent. This is terminology and rules that you just have to know. If you accept electrons, you are the oxidizing agent. So that makes sense. If you donate electrons to something else, that thing is going to become more negative. So you're reducing that thing. So that's why you're the reducing agent. If you accept electrons from someone else, you're making that thing more positive. So that's why you're the oxidizing agent. Okay? Because this stuff is really complex. So on like if they give you a multiple choice question, first of all, they can give you like a math problem. So you'll have to do the math here, which is not too bad. But then they can also give you a multiple choice question or a fill in the blank is what I've seen, where it'll be like 3 sentences with 3 fill in the blanks. And then you'll have to choose one answer with the 3 blanks filled in. And it could be like accept, donate, oxidizing agent, reducing agent. Standard reduction potential is more negative. Standard reduction potential is more positive. So after today's lecture, you should be completely able to answer all of those questions correctly. Okay? And then down here, this is also really important, recognizing reaction types. So we have 4 different types of reactions. We have oxidation reduction, which what did we learn about that? It's just giving electrons, accepting electrons. In these equations, how do we see the electrons? Do they actually say electrons? No. What are they? Hydrogens. They're hydrogens. And normally we see them in pairs of 2. So if we see one molecule that has like 6 hydrogens total, and then they have a little arrow, and then the next molecule only has 4 hydrogens, what do we know? It's probably an oxidation reduction reaction. Bam, we can get the right answer. So you have to know the terminology in order to be able to eliminate the wrong answers and end up with the correct answer. But you have to know all the terminologies. Okay, so oxidation reduction reactions are super easy. You can even see here, As an example that I gave you guys, we have NADH, and then here we have NAD plus. So we're missing a hydrogen. So yeah, oxidation reduction. That's why this is a redox pair. What about hydrolysis reactions? Well, that's where we have a water molecule. Hydro means water, so you should see an H2O come in. And then lysis means to break down. So whenever you see a water molecule, and then you have like another molecule that's broken in two, that's how you know you have a hydrolysis reaction, right? Okay, so you have to know what to look for. What about an isomerization reaction? This is an intramolecular rearrangement that results in the redistribution of electrons, but the overall oxidation state of the molecule doesn't change. You can have internal oxidation reduction events that don't change the overall charge, or you can have a double bond. You can go from cis to trans, or the position of the double bond can change. So these are pretty easy to see, to identify the isomerization reactions. One example that professors love to use are amino acids. You know how we all have like an L versus the D? So that's a common one. And lastly, we have the group transfer reactions. So I think this is going to be the hardest one for you guys to study. So day one, do you guys remember video one, how I told you guys memorize your functional groups? How many of you were able to memorize all your functional groups? Not too many, right? And that's okay. I understand it. It's a lot. For those of you who did this part, it's not going to be hard. It's going to be easy because you already know them. For those of you who didn't have a chance to, try to focus on these. Try to focus on the acyl group. Try to focus on the glycosyl group and a phosphoryl group. We're all pretty familiar with the phosphoryl group. I've drawn it on the board like 50 times throughout the semester, but these are the most common group transfers. And I want you to memorize these functional groups because otherwise you won't be able to get this question correct on the exam. Okay, I want you to just see it and be like, oh, that's an acyl group. And it was in this molecule, it was attached to the phosphate, and now it's attached to something else. So that was a group transfer reaction. You're going to be really good at that if you memorize those functional groups. It says some involve a nucleophilic substitution at carbon 1 of a sugar. If you guys missed the sugar problems on the exam, if you don't know where carbon 1 is supposed to be, when you have an aldose versus when you have a ketose, go back and review that material because it's coming up again. So when you ask if the final is cumulative, technically it's not, but really it is. You can see that here. Because if you don't know where the carbon 1 is on the sugar, you're not going to get the right answer here. Okay. Okay, we have 4 more minutes. Does anybody have any questions?
Is it actually like non-cumulative, so it's only the stuff after checking?
That's what the professor said last time.
Okay.
Double check with her, but that's what we said at the lab meeting.